Tanya was telling me she's been at Columbia for 12 years. Is that 14 years? She's a professor running a very active research group, specializing frequency metrology with ultra-cold molecules, most recently, which she's going to tell us something today.
What needs to be done?
Just yeah.
Okay. Can you hear me? I hear some sort of echo, maybe, because sorry.
Sounds fine to me.
Sorry, let me just reposition the mics. There's some interference, I think. So, how about now?
Still sounds fine.
Okay. Okay, then. So, if you don't complain, I'll continue. Thank you very much for your invitation and for the introduction. I gave a seminar here quite a few years ago, but it's really nice to be back after this long break. As advertised today, I'll talk about some of our experiments, or a subset of our experiments at Columbia. I'll focus on one direction, which is frequency metrology with ultra-cold molecules through quantum state control of ultra-cold molecular systems. So, as most of you know, molecules are really exciting frontier in quantum science. Basically, working with small molecules allows us to do many of the things we can do with atoms, but do them better, or much better in some cases. So some examples of things that we can do are engineering quantum materials with longer range interactions, or in engineering qubits. Another direction that our lab is also working on is applying molecular state control to questions in fundamental physics and high precision measurements, as well as metrology. And of course, with molecules, we can begin answering some fundamental questions in cold chemistry, the quantum nature of making chemical bonds and breaking bonds. So with all this, it's extremely useful to be able to get molecules to the ultra-cold regime. And so the question is, why should they be ultra-cold? Well, molecules have a lot more degrees of freedom than atoms. And for most of our applications, we would like to control exactly what quantum state they're in. So their energy structure actually corresponds to a very wide range of energies, starting with the electronic binding energy on the order of tens of thousands of degrees Kelvin, and going down in energy scale. Then we have vibrational energies at hundreds of Kelvin typically, then rotational energies at sort of fractions of a Kelvin. And then in many molecules, there's also hyperfine structure at microkelvin to millikelvin. And so in order to be able to control all of these degrees of freedom, rather than working with thermal samples, and also to, importantly, to be able to hold the molecules in very versatile optical traps, whose depths are typically on the order of tens of microkelvin. That means we would like to create samples of molecules that are in this range of single microkelvin or less. And then in our lab, we use these samples again for ultra-cold chemistry and for fundamental physics and metrology. Generally, there are two pathways to producing samples of ultra-cold molecules, and we use both of them in our lab. One is laser cooling directly small molecules, usually diatomics, more recently also bigger molecules. And for that, usually what we do is take a molecule with what's called optical cycling center, an alkaline earth metal atom such as strontium or calcium, that atom is bound to something like a halogen, like fluorine, or a hydrogen, as in our case. And then those molecules possess the feature that can repeatedly scatter photons, and then we can laser cool. So that's one approach. It allows a fairly wide variety of molecules to be laser cooled, but it's still technically a little bit challenging for many molecules. And the second approach, it relies on our now well-developed ability to laser cool atoms. And so usually either one type or two types of atoms are laser cooled, typically from the group 1 alkalis, and then they are assembled into diatomic molecules using using magnetic fields or optical fields. However, we would like to have access to a slightly wider variety of molecules that are ultra cold and are constructed using ultra cold atom assembly. In particular, we use atoms from group 2, specifically strontium atoms that are laser cooled, and then we assemble them into dimers. And the reason for that is that the strontium atoms have very nice spectroscopic features that many of them transfer to dimers that we work with in the lab. So, which I'll mention a couple of these advantages in a minute. So how do we create the dimers? Well, we start with laser-cooled atoms at the temperature of roughly microkelvin. So their speeds are about 10 millimeters per second. And then we rely on optical transfer with one stimulated step via an excited virtual state and one spontaneous emission step to end up with very reliable samples of bound molecules in the electronic ground state. These are right after the creation step. They're still fairly weakly bound, but they are properly bound molecules, just in a fairly high vibrational state, but in a very low rotational state. And the nice feature of this molecule assembly process is that the outgoing light carries this excess binding energy that you see here. And so the resulting molecules are on the exactly same order of magnitude of temperature as the atoms that we started with. So the atoms that we make into molecules are trapped in an optical trap, specifically in a one-dimensional optical lattice, which is a standing wave of light that holds the atoms in the in these bright microtraps, and the molecules are created there as well. That's for the metrology that I'll talk about today. It's a very kind of critical feature that we need the trap, as you will see, in order to confine the molecules and prevent them from moving while we probe them. On the other hand, when they're trapped in this bright standing wave of light, they are continuously exposed to very bright light, which can cause shifts and decoherence. So to mitigate that, it's really important to ensure that the optical lattice is what's called magic, or as magic as possible, meaning it doesn't cause decoherence between clock state superpositions. And what that means in practice is if you have two states that you're worried about, whether you're making a qubit or a clock, you can call them states 1 and 2. In the trap, in a magic trap, both of these states would be exposed to the exact same trap depth. So that's kind of the concept of a magic trap.
Tanya, can I ask a question?
Yes.
Yeah, this is Bill Phillips.
Go ahead.
So now, when you make the molecule with this process of spontaneous emission, you've got a recoil from the spontaneous emission. Is your lattice typically in the Lambdicki regime, so you don't get excitations due to the recoil, or doesn't it matter, or what's the deal there?
Yes, they're still certainly in the lattice after formation. I think the effect you're mentioning results in the molecular temperature being twice as high as the starting atomic temperature. So if we start with 1 microkelvin temperature of atoms, when we make molecules, then we have 2 microkelvin temperature molecules, basically. But they're still trapped in the lattice, because lattice is much deeper than that. Okay, so the experiment looks much like an atomic clock experiment that's based on strontium atoms, mostly lasers. In fact, a lot more lasers now than what is shown in the picture. And so we end up with these very cold diatomic molecules. I call them van der Waals dimers because the alkaline earth metals are fairly weakly bound. They're proper molecules, but they have fairly weak binding energies here in the ground state, about 1,000 wave numbers, and the binding is very follows very much the van der Waals force law. In fact, these are the only van der Waals molecules that are available currently at these microkelvin temperatures. And they have two very nice features for metrology. One feature is that strontium atoms, as you probably know from hearing about atomic clocks, they have these narrow spin flip or intercombination transitions from the singlet S ground state to the first excited triplet P electronic state. And these transitions are quite narrow. And when you form molecules, these molecules, at least weakly bound ones, they quite faithfully inherit that nice property. So that gives us a handle on very precise optical control of these molecules. The second feature is that the ground state, which is composed basically of two completely spinless atoms, one is 0, and the isotope that we use, there's no nuclear spin. That results in a very simple ground state potential. Again, it's pure van der Waals with no hyperfine structure. For metrology, it greatly simplifies metrology and also enables benchmarking and comparison to ab initio quantum chemistry calculations. So just to illustrate that, here's a ab initio, just the Born-Oppenheimer potential shown in red points compared to experimental potential found some years ago via classical spectroscopy, but the agreement is at the percent or sub-percent level, which is quite good for ab initio calculations, especially with such large, fairly large atoms like strontium. The one feature I mentioned is the availability of this very narrow line control. And that gives us a really nice tool to characterize the trapping environments of the molecules and also their temperature. So firstly, when they're trapped in the lattice and you probe along a tight confinement direction, you see these that there's no Doppler broadening because they're pinned, but instead you see trapping sidebands that are well resolved. Oops, so if we have narrow transitions, then the so-called carrier transition can be arbitrarily narrow, and then instead of, again, the Doppler broadening, we see the red trapping sideband and the blue trapping sideband, and that allows us to characterize the trap intensity very precisely. Also, it allows us to characterize the temperature of the molecules, which is not always easy to measure. And the traditional way to look at temperature when you can see sidebands is to take the ratio of the red to the blue sideband, but that gets a little bit finicky, especially as you get colder and colder and the red sideband gets smaller and smaller, then the ratio becomes poorly defined. The area of the sideband becomes quite difficult to find precisely. So then we can change the method and actually do very accurate thermometry by looking just at the carrier. So the spectrum you see at the top is taken at magic conditions. So you see a very sharp carrier, but it's possible to then shift the lattice conditions away from this magic value, and then you get a broadening of the carrier that is asymmetric and reflects the thermal distribution. And so we know exactly what that looks like, and from fitting it, we get very accurate determinations of temperature that are much better than just looking at the sideband ratios. Another application that we use relating to this feature of having narrow lines is we use it for imaging our molecules. And for imaging, we use photodissociation that works on these narrow transitions. So generally, direct imaging of molecules is much more problematic than direct imaging of atoms, because if you shine resonant light on the molecule, it generally will scatter one photon and then fall into some other level, and then it becomes dark. So you don't get a very good signal. So what we do instead is we take our molecules, and prior to imaging them, we use a photodissociating light pulse, so that the molecule breaks apart, and then we image the fragments. And now that's much better, because the fragments are now atoms, and they scatter many, many photons. And so this is how we generally do any kind of detection when we do clock spectroscopy or any other spectroscopy in the trap. And this study of breaking the bond using narrow line photodissociation actually was a whole big detour that we took in our research a few years ago. That was quite interesting in itself. Question?
Sorry, I just missed why the molecules scatter much less photons.
Just because molecules have lots of vibrational levels. So once you scatter a photon, it's likely to fall into a different vibrational state, and then it doesn't see your excitation light anymore after an average 1 photon.
But if you were if you were using the technique that you described, where you laser cool the molecules directly, then presumably you could use that same feature to scatter many photons off the molecules.
Yes, that's right. In a situation where you have a cycling molecule, then you can image it. But these molecules that are assembled from laser-cooled atoms generally don't have that feature.
Right.
Yeah.
So how do you tell the difference between a molecule that has been photodissociated and is now scattering photons, and just strontium atoms that fail to form molecules and are scattering?
Right. So yeah, the question was, how do we tell apart the dissociated molecules from pre-existing atoms? One is to do it visually. So I'll show you maybe one slide on that. That is kind of a nice way to do it. But otherwise, the simple way is just to clear out the atoms. So we can send a clearing pulse that just cleans all the atoms out. And so then we have a zero background measurement, and then whatever atoms reappear, that must be from the molecules. Yes, so just again, 1 or 2 slides on this process of using narrow line for dissociating molecules. For us, for the molecular clock, it's a tool. Just because we have to image, we have to count how many molecules are left after spectroscopy. But in itself, it's a very interesting process. So specifically, photodissociation, you can view just as a regular transition from some molecular bound state to a continuum state. For example, this is an excitation from the bound ground electronic state to the continuum where one of the atoms are excited. You could also do a 2-photon dissociation back to the ground state, or there are many variations of this process. And if you visualize photodissociation as a spectrum, then it looks not as a peak, but more like this threshold function, where below the threshold, you're not seeing any atoms, any fragments, and above the threshold, you suddenly are seeing a lot of them. And the nice thing about using narrow line for this process is that this function, the threshold, is very sharp. So basically, we can make it as sharp as about 1 kilohertz, which means the resulting heating of the fragments is on the order of nanokelvins. So basically, we can break the molecules apart with extremely low kinetic energies, which is maybe we don't care about this here, but it's a very useful application potentially for cold chemistry. So when we dissociate, we just use absorption imaging. And so we were looking on the side of the optical lattice and seeing these dissociated atoms emerge out as kind of clouds, and then we can take pictures and count how many there are. If you look carefully, you quickly notice that it has structure. So firstly, it has shells. Secondly, it has some angular structure. For example, you're seeing fragments go out vertically, but you're not seeing anything going toward the camera. So after a while, we got curious why that was. And we mounted the camera rather looking into the optical lattice, kind of with the same axis of symmetry rather than looking from the side. And then we could really uncover what was going on with the angular distribution. So you can see kind of a two-dimensional image here, which shows very clearly this dipolar-like pattern and multiple shells. And here's just a 3D reconstruction. So then we spent a couple of years wondering what is the origin of these angular distributions? And that led to itself to a kind of interesting realization that this state-resolved photodissociation, or the most basic form of what you might call photochemistry, is actually a very kind of promising, very rich method to look at what's going on with molecular bonds at very cold temperature. So just very, very briefly, photodissociation, you can think of it as a kind of very simple reaction or process where you take a molecule and add a burst of light, some photons, and what you end up with is the two fragments, where one of the fragments may be in a different electronic state. And so what this is basically a reversal of a collision process, right? It's an anti-collision where you start with a perfectly defined quantum system. You have a molecule in a specific quantum state. And light, of course, you can control its polarization and frequency really well. So there are no unknowns on the left side. So then your reverse collision, your anti-collision, also has no unknown quantum numbers. So you can create very interesting partial waves and their projections. And so that's what we saw. And as a result, you can see these these ultra-cold features of this reaction, like interference of matter waves that you normally can't easily create. So again, this is the system that we use to detect these photofragment distributions. We have the optical lattice in the one dimension, and then the photodissociation light shines along that axis, and then the fragments leave the lattice and kind of go outwards, as you can see with these green clouds. And then they're intercepted by a very wide imaging beam, which is just an absorption beam. And the absorption image is then projected onto a CCD camera. And because the camera is looking into the lattice, then we clearly can see the angular distribution, specifically this polar angle theta. And so then we can create really a variety of these anti-collision states. So a couple interesting ones are shown here. For example, this one has a partial wave 4, so it's a G wave. Angular momentum of the two particles is 4, with a combination of its projections of plus or minus 1. Because there are two quantum states and they interfere, you clearly see a non-dipolar. So you see a kind of a multi-part fragmentation pattern, which is only possible for a diatomic molecule if you have matter wave interference. Otherwise, you would have just two lobes. So this is the image, and this is the prediction. And these are a couple of different ways to show the same prediction, one on a sphere and one just as a kind of angular blob. And basically what this is we're just looking at interference of spherical harmonics that we constructed with these molecules. And same here, exactly the same experiment, only we designed a different anti-collision state, also G wave, but a different combination of its projection, and so that leads to a different interference pattern that we also observe as predicted. So it was a lot of fun playing with these, and just shows us that we have a lot of control, a lot more control when we can make molecules first, rather than just looking at ultra-cold atom collisions, which is also a very, very fruitful method, and we've learned a lot using atomic collisions, but the control is really enhanced when you can make a molecule and put it in a specific quantum state and then fragment it.
Tanya, this
Yes.
is Bill. Now, usually when we're thinking about collisions of cold atoms, because everything is so cold, we restrict the collision to S wave, maybe a little P wave. So here you got much higher angular momentum. And so I presume that you see these things because of something having to do with the fact that you're putting the light in. But could you say a little bit more about why you can get high angular momentum when, if you were looking at the reverse process, the actual collision, you wouldn't?
Right. Yeah, that's another thing that would be very difficult to do with atoms. Like you said, if you make atoms cold enough, then you can see S wave. And certainly we can also make S wave here, then you just get an isotropic pattern, J0, a typical isotropic outgoing pattern. But if you were to have to look at collisions of atoms, and you wanted to collide, G wave with very specific projections, that would be just very difficult to create. But here we can create them very easily, as long as we find a proper starting state. So we make initially we make molecules in J0, but we also make some in J2. So we just, for this experiment, we would start with those, and then with 2 optical photons, you can get to 4. Okay, so 4 is actually the biggest one we could get to, but just playing with quantum numbers and selection rules, we can get to any J from 0 through at least 4 and almost all values of M. And again, that would be very difficult to do if you were just going with collisions rather than reverse collisions.
Right, thanks.
Mm-hmm. Right. Yeah. So again, just to compare these kind of cool multi-lobed patterns with something you would expect when you fragment a diatomic molecule, kind of quasi-classically, you would expect a dipolar type pattern, which we of course do get also in some experiments. So some experiments lead to just spherical harmonic Y01, that is a dipolar pattern. Okay, but we can get also much more interesting ones. And just to mention one other trick, one other thing we can do with these molecules, after we create them in a fairly weakly bound state, we can then controllably place them into the most deeply, the absolute ground state. So that's for that we use what's called stimulated Raman adiabatic passage or stirrup. It's a fairly common approach to do this for bialkali molecules, but here it works also with these bialkaline earth dimers. So we start with all molecules in the most weak, the V-1 most weakly bound state, right under the threshold. Then we sweep 2 colors in a certain temporal configuration to coherently bring all the molecules to the ground state, absolute ground state. We don't see them here, but to see them, we can reverse the process and then we recover most of them. And nowadays we can do this process with about 90% one-way efficiency. So that gives us access to, again, to molecules in the absolute ground state. So then we can do the clock using that as one of the clock states. And also we can study ultra-cold collisions then in the ground state. So that's a really nice, useful tool. So I promised to tell you a little bit about metrology using this system. Basically, we use these molecules to demonstrate a kind of clock. So what we mean by quantum clock in general is that you have some kind of ultra high Q, very stable oscillator. Usually it's a laser or a microwave source. And then that is steered to some absolutely well-defined frequency, either either be an optical transition or sometimes a microwave transition in an atom. So this is how most clocks work these days. Or in our case, we use a vibrational transition, a 2-photon vibrational transition in a molecule, which is separated by a terahertz scale interval. So the transition is all within the same electronic state. So the electronic configuration does not change. The only thing that changes here is the vibrational excitation of the molecule.
So does that have an advantage for zeroing out black body radiation shift?
Yeah, so I will discuss the systematics and we can discuss in more detail what kind of advantages there are, but there certainly are some advantages over this configuration over the atomic clocks. But first, I'll motivate this using maybe more basic physics. Why would we like to have an atomic clock? So one application that we are excited about is interatomic force sensing with a very high precision. So basically, if we can map out all these clock states, meaning all the bound vibrational states with a very high precision, let's say sub-part per trillion, or it could be much better than that, then we can invert the spectrum to obtain the potential. In other words, the interatomic force, also with a comparable, very high precision. And this can be used to as a test, a tool for new forces, as a kind of tabletop experiment, one of many that looks at potentially new physics using a simple setup. So just to kind of visualize what you would be looking for, you can picture the diatomic molecule as kind of two heavy atoms connected by the bond, which if we vary the vibrational states from 0 to the top, that varies the separation or the bond length from about 0.5 to 5 nanometers. So we get an order of magnitude in length. And then we can look, for example, just at mass-dependent interactions. So normally you have some gravitational interaction that we know from Newtonian gravity, but there could be something on top of it due to new particles or new forces. And at the nanometer scale, existing experiments cannot test this very well. So basically, A is almost unconstrained from existing scattering experiments. We know it's less than 10 to the 22 or something like this, but it's still a huge compared to 1. So any system that allows us to improve on this at the nanometer scale actually allows us to see something new. And that's just one application of molecular clocks. But of course, from the metrology point of view, that kind of opens the door to terahertz metrology, which is kind of a dark window right now. We have microwave, we have optical, not much in the terahertz. Also, molecules are really promising for further studies of variations of electron to proton mass ratio and things like that.
Tanya?
Yes.
You so you mentioned this as being a good way of looking at short-range deviations from Newtonian gravity, but admittedly, being a long way from doing that. But can any of these experiments realistically see even the Newtonian part?
Well, so when I say this magnitude of the new potentially Yukawa potential is constrained to worse than 10 to the 20, that means that existing experiments, which is mostly cold neutron scattering, they can see 10 to the 22 times big G, right? So that's how far they are from seeing the effect of G. So anything better than that would help us constrain this parameter space better. You would not use this experiment to measure big G at this point because it's not very sensitive directly, but it can constrain new forces that are predicted by some theories to arise at very short scales.
So within your lifetime, time, what do you think you'll be able to do?
Well, we would like to just do kind of one full analysis run, and that will benchmark it to. I mean, I hope to be able to do better than certainly any of the existing ones, but I don't want to throw out a number. We experimentally, as you will see, we basically in a position to do this. We need some theory help, which we are getting now. So I think largely it depends to how well some ab initio theory can be done on these fairly large atomic systems. So maybe I won't give you a number, but we hope to do better than the existing limits, but also in the meantime, come up with a really nice alternative clock.
Okay.
Yeah. So basically that's some of the physics motivation. The conceptual implementation of the molecular clock is quite simple. Again, the only important electronic state is the ground state, which is a single curve without any complications. And we use two of the rotation-free bound states. So one of a lower lying vibrational state and a higher lying vibrational state that are coupled with two photons off-resonantly via an excited state. And while we are probing, these molecules are held again in an optical lattice trap, which has to be magic. In other words, both clock states must see the same shape and depth of the trap, such that there's no decoherence when you make superpositions of the clock states. To give you just a little bit more detail in order to understand how the clock works, I just added mostly more detail to the excited state. So again, this is the ground electronic state, and you can call state 1 is the upper clock state, state 2 is the lower clock state, and then the probes, this what we call the Raman transition, the clock probes, they couple off resonantly from one of the states that are shown here. And these two excited potentials that I'm showing kind of fragments of, they all correlate to the first excited state. That would be singlet S plus triplet P. Okay, and then another important feature, of course, as I mentioned, they're held in a lattice. So we need to understand the effects of the lattice light, the trap light, on the clock states. The lattice is red detuned from this first excited threshold. So it lies lower. You can visualize the lattice as kind of being sort of near resonance between the lower clock state and one of the bound states in this excited potential. So there are two main potentials here that correlate to that same threshold. And in order to engineer a magic lattice, the one that doesn't perturb the superposition of states 1 and 2, then we have to choose a specific operating condition for this yellow dashed line, which is the lattice frequency. So you can look at the molecular states that are relevant. There's the lower clock state in blue, the upper clock state in red, and the green is the state that is closest to what the lattice interacts with. And generally, when you place the molecules into an infrared kind of lattice, because molecules are polarizable, the lattice is red detuned. Generally, it traps both clock states. So their start shifts are both negative, they're both trapped, but generally they will be trapped by different amounts. And this causes a frequency shift and also a dephasing because they see different intensities in different parts of the trap. However, when we tune the lattice to a specific point not far from this green resonance, specifically, it's a little bit blue detuned from the green, from the blue to green resonance, then the lattice itself stark shifts the green state, which we don't really care about, and the blue state. So it brings the blue state up. And when we tune the lattice frequency just right, now the trap depth that I call U here starts to match the new trap depth of the blue state, and then we get a magic trapping condition. And under this condition, we expect yes, right. So this magic trapping condition means that as you vary the lattice intensity, you see almost no shift. So that's one empirical way to look at this. So the different colors are the different lattice wavelengths or frequencies around that nice point. And for most of them, there is some shift as you vary the lattice power and look at the kind of clock frequency fairly coarsely here. But at some point it gets very flat. So that's marked with a star. So that red line corresponds more or less to the magic wavelength. And
10 more minutes.
okay. Oh, okay. Okay. So then I'll go a little bit faster because I wanted to talk a little bit about the key systematic effects. But basically, when we tune to the magic wavelength, we see directly that the lattice does tune the trap depth of that lower state. And we see the nice dispersive feature that we expect. And where the green line, the vertical line is where we expect the trap depth of the lower clock state to match that of the upper clock state. And we see that by looking at the resonance width. And as expected, it drops very dramatically at that point. So we start off at about 0.1 megahertz, which is broadened by the decoherence through the lattice. Then it gets much worse at the resonance, and then it gets dramatically better where we expected. And we see that by looking at clock resonances, which are kind of broad elsewhere, but at that point, it becomes very symmetric and very narrow, as I'll show here separately. So we see then at the magic wavelength, we can see clock resonances at about 10 hertz wide. So that would correspond to the quality factor of 3 trillion. Just to compare it actually with the intrinsic Q factor, which would be limited by natural decay and or black body radiation. For these vibrational states, that's extremely high and actually much higher than for atomic clocks. So we're still very far from matching that, but that kind of gives us, some inspiration that we can control this much better yet and get a really excellent clock. But for now, we are happy with 3 trillion in this kind of first demonstration. In practice, when we do clock systematics, we use this kind of 30 millisecond pi pulses, which broadens the peak to about 30 hertz. So that's the black one you see. That's sort of what we use for current operating conditions. Another way to look at the clock coherence, again, is looking not just at the peak resonance, but making it do Rabi oscillations in a controlled way. So here, the Rabi oscillations are between a tightly bound state and a weakly bound state, and it flops for about 100 milliseconds. And then there are 2 key decoherence processes that I show. One is due to collisions, because we are not protecting the molecules at the moment, but that's not yet the dominant one. The dominant one is due to the lattice scattering, and that's the one that we need to improve to make a lot of progress going forward. So the collisional one is pretty well understood. Here, the collisional decay is shown using and fitted using a 2-body function, which works very well. And the collisional rate is quite consistent with other ultra-cold molecule systems. That one can also be eliminated potentially by using 3-dimensional lattices. However, the other limitation, which is the lattice-induced scattering, is not extremely well understood because we were frankly expecting much less decoherence from the lattice. Now, for a magic lattice, there are many choices actually, because there are many states here that you can use to make a magic wavelength. And the best magic wavelengths where the coupling is the strongest. So if you make this chart with all the ground states and all the possible, those 1U excited states, you want to choose the ones with the brighter color, the strongest coupling that will give you the least scattering. And so if you zoom in just on the bottom, because we want a deeply bound clock state, then you get this kind of checkerboard-like pattern, and you want to choose the brighter pairs for using for the lattice. So we did experiments first with the white rectangle, then a slightly better one, that a slightly better coherence down here. The best one is down here, which is what we did with the final iteration of the clock experiment. So we've sort of tried to zone in on the best choice for the magic wavelength, which again, luckily there are many of. Even so, the scattering is much worse than is expected. The expectation here, so for some measure of the lattice light intensity, the scattering rate is shown in green. So that's what is expected from a one photon process. What we actually measure is shown with the black points. And as you can see, it actually fits a parabola and not a line, which tells us that probably there is some two photon scattering, which is important for molecular systems, potentially much more than for atomic systems. So that's something that is also fundamental to other experiments that use cold molecules and optical tweezers and optical lattices. And that's something that needs to be better understood. So, and now I would like to show you the result of the clock evaluation, sort of our first clock run, to tell you what are the main systematic effects and how good the clock is at the moment. So all the values here are in units of fractional units of part in 10 to the 14, which is more or less kind of the precision of atomic clocks as they were maybe 1.5 decades ago when we were starting to work on them. So here are the systematic effects we've looked at. Overall, the uncertainty is below 5 parts in 10 to the 14. So that's where we are. And the some effects like the Zeeman effects are expected to be actually much more well controlled than for atomic clocks. So we are much less sensitive to things like that. The more challenging effects are the stark shift due to the lattice, the two probe beams, and also molecular density and molecular collisions. So I'll just I won't talk about all of them, but just a couple of key ones that maybe we learned a lot from or were surprised by. One is the clock shift due to the lattice light. So here is a much better resolved picture that I showed you before with the colored lines. Now this is at the hertz level, no longer at the megahertz level. And you can see clearly that they're not lines, but they're very clearly parabolic. So as we change the lattice trapping power or intensity, we very clearly see higher order stark shifts, which is hyperpolarizability that arises at a much stronger level than for atomic transitions. And so we can also plot just the linear part, alpha. Technically, magic wavelength is, magic wavelength is where alpha is 0 here. However, our operating intensity, our operating polarizability is not 0 because we have to choose one that is flat, not at 0 intensity, but flat at the operating lattice intensity. So this balance between second order and first order polarizability kind of forces us to choose a lattice frequency that is not perfectly magic. So I think that's what currently is the biggest limitation to this clock, and that's something that we're working on to improve. Still, the uncertainty to this leading effect is just 4 parts in 10 to the 14. The second one is due to probe light power. So again, we have 2 probes, what's called here up leg and down leg. And these are fairly straightforward. These are very linear. And so we can actually extrapolate them from very high intensities down to operating intensities. And although the uncertainties is fairly high right now, it's just a technical reason that one of the clock intensities could not be taken very high, but in principle that can be done, and we are not currently limited by this systematic effect. Also, you see that from the two colors, the shift go in the opposite directions, if you choose the detuning with the correct sign up here, so that there's actually a relative cancellation of the two stark shifts, and they can be the first order zeroed out. Okay, another tricky one to evaluate was the density shift. So we did manage to constrain it to a few parts in 10 to the 15. As you can see with the pretty good Gaussian, there's just a little offset from 0. So surprisingly, there was a density shift at this level at about twice the value of the uncertainty. But the tricky part is that the molecular density goes down with time because they actually collide and react. So it was a little challenging to actually define what the density is. It's not constant. But again, in the future, we could potentially protect the molecules from collision, and then that could be resolved as well. But again, currently, it's not a limiting factor in the clock evaluation. I'll mention briefly the black body radiation. Again, at this point, it's not close to being a limiting factor, but actually this is an ab initio calculation of the black body shift for the different clock states, of which there are about 60. And we now operate from the least bound one to the deepest bound one, so there is expected to be a shift. But if these predictions are true, then there should be clock state pairs which are basically black body free. And so that's something that we are not sure if that's correct, but we are about to try and test it experimentally. So if you plot then the kind of use color plot to plot the black body shifts between different clock state pairs, so 60 of them on each axis, then you get this, well, this that line with low shift is a trivial one because it's between each clock state and itself. But then this diagonal line that goes like this shows that there could be many clock state pairs that are naturally black body free, which would be quite valuable if that is true.
What do you mean by black body free? Are these shifts?
So sorry, black body free means, yeah, so both clock states do have some shifts, but there's no net shift.
They're free in the transition rather than.
Yeah, the transition, exactly. The transition is free.
Each draw like a straight line across.
Yeah, exactly. So each state does have a shift of about 3 or 4 hertz according to this calculation, but their difference could have a vanishing shift. Okay, and then finally, we did compare this clock to a cesium time standard using kind of not a, maybe not a NIST quality approach, but something we could do in New York City, which is kind of put an antenna on the roof that talks to GPS satellites, and then we had a time interval counter that receives pulses from the GPS receiver and receives pulses from our very old school rubidium clock box. And then we compare them and kind of post correct that. And that, that comparison to cesium was, of course, the limiting factor in our clock evaluation. So you can see these are a few trial runs. Somewhere my pointer went away, but here you can see maybe 10 trial runs, and the systematic and statistical errors are the small ones, and the cesium comparison errors are large. So it's only a 10 to the 13. Of course, the main point for us was to characterize the clock itself. So it's the systematic effect. But now that we have compared it to cesium, it can serve as a kind of terahertz reference. So just to conclude on that, here are the frequency standards that were recommended around 2017. With the uncertainty, the higher the bars, the more tight the uncertainty in this case. So you can see in the terahertz, again, sorry, the pointer is not really working, but in the terahertz, you can see only these two molecules, OSO4 and CH4. And our molecular clock is up there, even if you limit it by our comparison to cesium, it's still 10 to the minus 13. So it goes right there. It's 30 terahertz, so it would be right near OSO4 and a little bit more precise. So I think it could be a nice contribution to terahertz metrology. And importantly, that was just the first run. So there's basically, if we can figure out what's going on with the excessive lattice scattering and increase that coherence time, then the natural lifetime is basically limitless, and the clock can be made much more precise and much more accurate. Already we can get started with this project of looking at all the bound states and their energies, because this precision is more than good enough. We've already coarsely found all the clock states, so their energies are shown in the top graph, and the bottom graph just shows their deviation from some theoretical kind of theory/experiment expectation. So now we just have to do this not at tens of megahertz level, but at a hertz level. And again, experimentally, we're well in a good place to do that. Okay, so I think I can skip the summary and just thank my research group who worked very hard on this experiment, especially Con Leong, who is not in the picture. He just defended last month, but he was kind of instrumental in characterizing the molecular clock. And I would like to thank our theory colleagues, particular Robert Mashinsky's group at the University of Warsaw. And thank you for your attention.
Well, that's precise time metrology at its best.
Thank you.
So much.
Yeah.
I'm sure there are questions. Yes. Alex.
Thank you.
I have a question about matter wave interference. That was the middle of your talk there. Some of the color plots have this almost an inherent asymmetry when compared to the calculation, and so I missed it. Is there a reason for that asymmetry?
Right. So yes, I will say that qualitatively they agreed with theory very well. So I think we understand all the physics. There were some imperfections that we were not able to fix. I think a lot of this has to do with the imperfect wave fronts of the imaging beam, because it's a fairly large beam and we weren't controlling its beam quality to an extreme precision. So I mean, we tried to take differential measurements, but still we cannot always remove features on the wave fronts of the imaging beam. So that causes some brightenings in some places that you don't, of course, have in the theoretical modeling. Also, if there's some imperfect polarization of that beam, that could cause it. So I think that's artifacts. I think the physics is understood. Sure.
Let's alternate questions between live and online, if there's someone online.
Yes, this is Paul Julian. I'd like to ask a question. Very beautiful work, Tanya. That's a wonderful clock. Curious about your 2-photon scattering problem. Are any of your ab initio theorists trying to calculate what that rate is to see if it more or less agrees, if they can understand that rate theoretically? Oh,
I would be very, very happy to have that. Actually, yeah, Robert's former student who unfortunately finished up by now, yes, she tried to calculate it, and yet just unfortunately it requires some knowledge of the doubly excited potential, sort of higher lying potentials, and the results seem to indicate that anything is possible basically from 0 to something more than what we are seeing. So I think it was a good effort, but it just didn't really narrow things down for us. So, but also that wasn't the main project of the student. So I think if somebody could help us with that, that would be really useful.
Thank you.
Question?
Yeah.
Yes.
So in calculating non-magic effects, how much do you have to worry about the sizes of the highly excited vibrational molecules differing from the ground state and exploring different stark shifts?
Could you repeat the question?
Sorry, maybe I didn't. Are you referring to? Sorry, you're referring to clock systematics, or you're referring to the photodissociation? Okay, and so you were wondering because they the spatial extent of the quantum states are different.
Yes.
Well, I mean, we are studying clock systematics like we would in an atomic clock, right? These are 2 quantum states, so they are, perfectly defined. So we just look at their shifts versus different physical effects. Yes, so they do occupy slightly different sizes, but I mean, yeah, so ultimately that will be maybe a part of our analysis when we try to search for these new forces. But as far as clock evaluations, we just treat them as well-defined clock states, and then you can turn different knobs and look at the shifts just like you would in an atomic clock.
Online question? If not, live? Going once? Yes.
Yeah.
So, like with regards to the decoherence between the oscillation between two vibrational states.
Mhm.
So I guess is you're losing population like a transition to other vibrational states that weren't in this superposition.
No. So the decoherence, yeah, when I showed the Rabi flops that are decaying, the main limitation to that is the fact that they're being held in a magic wavelength lattice, and that magic lattice is somewhat close to a transition. So I said we had to engineer the wavelength to be at a very special detuning from some lattice-driven resonance. That detuning is only a few gigahertz, so it does scatter light, and it's expected to scatter light. It just scatters a lot more light than we expect. And that's the leading systematic, that's the leading systematic effect, partly because it limits our coherence as well. That's a main limitation to the coherence. Mhm.
Anything else from any quarter? Well, if not, let's thank Tanya again.
Thank you.